Hi, everyone. Welcome to the first of our deep dive TinyML auto machine learning tutorials. A few weeks ago, we had our really exciting TinyML auto ML forum with lots of attendees. And if you got to see any of that, we did very, very quick 3-minute demos, which is not nearly enough to explore a lot of the exciting parts. I'm Elias Fallon. I'm the chair of the TinyML AutoML working group. And so I'm happy to host and introduce our first deep dive with Neuton AI. But before we get started, we need to thank all of our Tiny Machine Learning strategic partners helping this whole organization and all of these companies take TinyML to the next level together. You can see all the logos there. If you are not already, please do join the continuously growing Tiny Machine Learning communities and on both LinkedIn and Meetup. It's a great way to find out more about all the things going on in Tiny Machine Learning. And subscribe to the TinyML YouTube channel. This deep dive and many other videos are available on there. This video, after we get done with the session in about a week, will be on there. So make sure and subscribe and keep up. As a reminder, there is another live event coming up this fall, the TinyML EMEA Innovation Forum 2022 in Cyprus in person in October. So go take a look at that and look at signing up or submitting. There's still call for papers open. So if you'd like to present, make sure and send something in. If you'd like to sponsor, contact the TinyML organization at sponsorships@tinyml.org and get involved there as well. And as a reminder, as I've just mentioned, the videos will be posted next week, youtube.com/tinyml. If you have questions during the presentation, use the Q&A box. We'll keep an eye on it and we'll make sure and try and get to those questions during the presentations or at the end and get those answers out there. So thanks very much, everybody, for joining us. I'd like to introduce the first speaker. Blair Newman has strong tech expertise and 20 years of leadership experience. He provides unprecedented insights into the future of AI's development and use. As Neuton's CTO, he is engaged in overseeing the business solution as well as ensuring high quality services delivered to the clients. So Blair, let me turn it over to you.
All right, thanks, Elias. And as always, I always appreciate the opportunity to have a chance to speak to the community. All right, so welcome everyone. I think as Elias mentioned, this is kind of we're kind of the tip of the spear as it relates to kind of going into these deep dive sessions. So just by way of introduction, as Elias mentioned, my name is Blair Newman. I'm the CTO here at Neuton. Neuton is our TinyML AutoML solution, but as an organization, we've been around for a little over 17 years. Myself, I've been with the organization going on a little over 7 years myself. I bring that to everyone's attention because our objective for some time, at least for myself as the CTO, being responsible for a number of our products and services that we bring to our customers, is, my mission has always been, how can I bring our products, our services to the fingertips of our customers? And certainly Neuton.ai, or Neuton, is one of the areas where I believe that we've been fairly successful at. Now, when we began this journey, I would say roughly 3 to 4 years ago, one of our primary objectives was how can we make machine learning available to everyone? And we truly and always meant this in a very literal sense, is we wanted to be the enabler for everyone, irrespective of your expertise, your capital position, whether it's resources or financial, as to how can we enable this community to be able to take advantage of machine learning. Now, over time, of course, as TinyML has began to pick up speed and grow exponentially, we have continued to kind of focus a little bit more in this particular area. And this is what we really want to share with you guys today. is how we've kind of taken the baton and began to kind of move everything forward. So one of the things that we will share with you guys today, and here will be at least our format. So I'll spend roughly 10, maybe no more than 15 minutes, kind of giving you guys an overview as to what we're doing in this particular space, the value that we believe that you guys will get out of, leveraging our platform. And then from there, I'll hand it over to Daniil. Daniil is our head of machine learning. He's also been here throughout the duration as we've built this particular platform. And I'll go into a little bit more details about that. So hopefully that kind of, at the moment, gives you guys a little bit of a helicopter view in regards to myself, our organization's mission, and then Daniil himself as well. So if we begin to kind of maybe take a step back to a few years ago when TinyML began to be defined, and I'm sure all of you guys know who are some of the key players as it relates to defining TinyML and really getting the TinyML organization going, moving forward. They really kind of laid out for us a number of different key criteria that they really wanted to check the box on as it relates to defining TinyML, whether it was the amount of total memory that was used, power consumed, the amount of processing that was available, and then, of course, just the overall cost. But we all know that when it comes to TinyML, your currency is space and the amount of power that you consume. So this was the vision that everyone kind of defined when we began this TinyML adventure roughly around 3 years ago. And now when we begin to kind of look at what we see today, is we actually do see a number of different projects. Just Hackster.io as an example, it's not limited to that. Well, what we began to see is that there were a number of different projects, whether they were posted, as educational or maybe even in production, that the size of the footprint of the models and the consumable memory that was being used was oftentimes more than 100 kilobytes. Some of them obviously were below 100 kilobytes, but for us, what we decided, or what we thought is, we know we can do better. And in order to achieve some of the goals that were set in 2019, as well as make TinyML available to everyone, we felt that we needed to do something different. We felt that we needed to flip the paradigm on its head as to how we were all approaching building models, the approach that you would take to build models and integrate those models into your respective devices. And not just limit the models or limit the devices that those models can be integrated in. But this, if you go and you look today, this is largely what we see. So we decided and we began to look at how can we now really begin to redefine TinyML as it is today. And there's a number of different definitions, whether you're talking about edge, TinyML, et cetera. And I don't think there's no reason for us to get into all of the details, but I do kind of want to cut to the chase. Our objective, as we begin to talk about enabling TinyML for everyone, and there's 3 boxes that you got to check that I mentioned, is our belief is that the definition of TinyML should be less than 10 kilobytes as it relates to your tiny footprint, as it relates to your total footprint, and the models that you are building should be less than a kilobyte. We believe that this creates a number of different opportunities that are out there and will help continue to accelerate the growth of TinyML, more importantly, from a production perspective. I always like to say, building a model that you don't put into production is just a shiny object. So what we're going to show you today is how we can enable all of you guys to build models with a total footprint, memory, et cetera, of less than 10 kilobytes, and that all of the models that you build in one iteration without having to go through any additional steps will oftentimes be less than 1 kilobyte. So this is where we say, and we're taking the baton and helping to accelerate the growth as it relates to TinyML. So once again, and not to, let's say, be redundant or anything like this, our definition as it relates to your total footprint is not only your model, and this includes all of your weight, your metadata, et cetera, your calculator, your pre-processing. This is what we've defined as your total footprint. So that's when we refer to those 10 kilobytes, we're referring to all three components, which you typically have to take into consideration when you're looking to embed your model into your respective device. So for us, it's 10 kilobytes or less when it comes to total footprint, and 1 kilobyte or less when it comes to your actual model size. Now, again, this is always our target. And this is something that we have seen consistently, that by leveraging our platform, we're able to produce for our partners as well as our respective customers. But one of the things that I also like to highlight, and I'm sure all of you guys know it. So if you kind of look at some of the traditional techniques that we've always followed for years, is oftentimes, you start off, maybe you're leveraging TensorFlow, PyTorch, et cetera. You build a model. That model size is not at the point where you're able to integrate or embed that particular model into your respective device. So then you have to take some additional steps in order to accomplish that. So whether you're going through quantization, pruning, and there's a lot of different techniques that are out there, et cetera, but they still going on what I would like to say, the old tried and true approach of starting with a fully connected model and then reducing that model size, whether it's pre or post training, because there are some good tools that are out there. But oftentimes you have to compromise your accuracy in order to achieve that size that you're looking for. Leveraging our platform, because we don't use TensorFlow or anything like that, we leverage an algorithm that we've built internally in-house. You don't have to go through any of those steps. You don't have to consider quantization, pruning, distillation, anything. All of the models that you will build leveraging our platform in one iteration will come out ready to be embedded into any respective device. And you don't compromise size and you don't compromise the metric. So oftentimes we're trying to find a balance between the two. So we said, one is not enough. We believe that we've produced a platform that allows you to get the best of both worlds. Now, one of the things that I've mentioned is that, of course, we have an AutoML solution. So we're looking to enable everyone. Are we looking to empower those who may already have the technical skills in order to build models manually? So our platform handles everything in the background. There's no coding that's required at any point to produce a model. So we handle all of this automatically, and we do it in one iteration. And I'm sure you guys know that oftentimes it's a very iterative process to find a model to reach the level of size and accuracy that meets your particular business requirements. And you don't have to perform any compression techniques whatsoever at any time by leveraging our platform. What we've seen consistently is that oftentimes we have models that are up to 1,000 times smaller than you may experience with leveraging some neural network frameworks that are out there, or leveraging some non-neural network frameworks that are out there. And we see this very consistently. Now, one of the things that we like to highlight, because there's two sides, there are some particular use cases where leveraging a neural network makes sense. There are some solutions or use cases where leveraging a non-neural network algorithm makes sense. And there's pros and cons to both. There are some limitations. As an example, if you're looking to leverage a neural network that is out there, where if you have 8-bit or 16-bit MCUs, you won't be able to leverage a neural network. With our platform, you can. So we support 8-bit, 16-bit, 32-bit. And as I've mentioned, no compression techniques are required. Also, all of the models that we're producing are silicon agnostic. But you'll oftentimes, when you're leveraging some of those existing frameworks, you'll typically have, as we know, a very large footprint. One of the things that we do is we never start off with a fully connected network. Every model that we build always starts out with one individual and single neuron, and then we build our models neuron by neuron after that. And we perform cross-validation along the way. So once we've reached the optimal size and the highest level of accuracy, we stop training and no further steps are required. And because of this, we result in models that are extremely small. Inference times are also significantly and oftentimes exponentially faster than what you would typically experience, maybe with other frameworks that are out there. And if you're leveraging some of the non-neural network algorithms that are out there, we kind of know some of those limitations. Oftentimes, you're not able to leverage those particular algorithms when it comes to some of the more complex tasks that you're working on. Or they'll also have a very large footprint, which will render them useless when it comes to, once again, looking to implement a TinyML solution. So we've kind of merged the best of both worlds, and we've been enabling our customers and partners, and hopefully we can have an opportunity to share this light with you guys as well, so that you can begin to kind of take advantage of doing something completely different than what has historically been done over time. And just for a moment, 100%, it is an eye chart. I have to admit it. But what good is saying that you can accomplish something without also being able to demonstrate the results? And I'm sure that we will have an opportunity to send out this presentation, this video, et cetera, and give all of you guys an opportunity to look at a number of different benchmarks that we've put forth on a number of different well-known data sets and problem types that are out there. And I'll go into, in just a moment, very briefly, a number of different use cases that we're actively working with or have worked with our customers and partners. But one of the things that you can consistently see is that our model sizes are oftentimes significantly less than what you're able to accomplish if you were to leverage some of the other platforms or other frameworks that are out there. And that's one of the things that we're extremely proud of. So when you begin to talk about making machine learning available to everyone, you want it to be able to check the box from a technology perspective. You want to be able to meet the expectations there. Number two, you want to be able to enable organizations, partners who may not necessarily have that data scientist available. They may not have those technical resources available. And we accomplish that with our AutoML solution as well. But technically is where we really define ourselves and differentiate ourselves as it relates to helping the TinyML community accelerate adoption. Now, I began to kind of touch on how do we accomplish this. One of the things that I mentioned is that we grow all of our models neuron by neuron. I also mentioned that we leverage a framework that we've developed in-house. But although oftentimes when you hear proprietary, it can be a bit of a boogeyman. All of the models that we produce, they're 100% open. They are silicon agnostic. So it's just our algorithm that we've developed and we've patented. And we perform cross-validation along the way. So no, our algorithm, our platform, you don't have to perform any manual search for any various parameters that are out there. But one of the things that we do, which enables us to have these compact models, is we take a very selective approach to which features that we connect to. And every time we connect one neuron to the next, then we perform that cross-validation and then determine which feature will have the next or the highest predictive power from there. And as we go on throughout the presentation, and as Daniil will give you guys a view into the platform, we'll certainly be able to go into some more details as you guys like. So just being aware of time. Here are some of the use cases that we are actively working on. So whether it's predictive maintenance, whether it's human interfaces, asset tracking and monitoring, voice activity detection, classifying sound events, glass breaking, etc., wake words. I would say that these are the areas where so far we find the most traction. Of course, there are many more different use cases that are out there as it relates to, looking to whether validate a particular approach, et cetera. But from a production perspective, these are the areas where we find the most traction, and we're always ready to work with our customers and partners on. Now, lastly, just summarizing, we have a SaaS-based solution. There's no coding, and we've automated our entire pipeline. Our pipeline has been automated and really streamlined into 3 clicks or 3 steps, which Janelle will highlight in just a moment. And more importantly, now lastly, the last checkbox when it comes to making our platform available to everyone, right? So we had the technical component. Now we're talking about from a financial component. We have a free unlimited plan for all developers, and we don't scale our functions and features, not at all. So you have the full flight and use of our platform, irrespective of your experience, to be able to take advantage of everything that you will see that Daniil will demonstrate in just a moment. And at this point, I'd like to hand it over to Daniil, and Daniil will begin to share with you guys Neuton, our TinyML solution. And I'm certain and I'm hopeful that all of you guys will enjoy what you guys will see today. So with that said, Daniil, I will hand it over to you.
My name is Daniel. I'm a data scientist here at Neuton. Today's demo is going to be based on the use case that we have where we have trained a model to recognize air writing digits. And we've got a project here on Hackster that explains all the details of the actual model creation with our platform. And just before we dive into the platform, which is this one right here, let me just quickly show you 2 very fast videos from this project, just to explain how the data has been collected. This first maybe 20-second video is very short. So our engineer, this is him and his the device that he was using for collecting the data, and he was creating 200 samples of each of the 10 digits from 0 to 9. And that way he had collected the necessary data from 3 axes of accelerometer to train a model that would recognize whatever the person is drawing in the air with such a model built into the device, for example, into the Apple Watch or something. And the last video is the inference by this model. So after the model has been trained, we have embedded it into that same microcontroller. And if you can see right here, so he's drawing 1, and you can see the probability 100%, the model recognized correctly. So the second digit was recognized with 78% probability, 98% probability for 3, and so forth. It is going to recognize all the 10 digits more or less accurately. So hopefully this gives you an idea of the model that we are going to build just now. So now let's switch over to the platform. Here it is, and let me make it full screen. So this is the main workspace, and it's tile-based. And as you can see, I've got lots of different models that I've been training, really about 30 of them or so. So this just gives you an idea that you can start as many machine learning projects as you like simultaneously, because some of them may take quite a while. For example, some audio processing models and wake words detection, they can be training for hours and maybe days, depending on the data size. But it really doesn't matter. You start a new solution, you upload your data, you start training, and then you can jump back here into the main workspace and work with your other projects or create additional projects, because for every one of them, a dedicated infrastructure will be deployed on the Google Cloud just for the time of the training process, and then it will be shut down and all the artifacts of the training will be saved. So to train a new model, you click this button here, add a new solution. You just give it a name. Let's say demo. And the three steps that Blair had mentioned, well, here they are. You upload your data, you configure and perform training under the training tab, and under the prediction tab, you can download your model and look at some analytics and all the other things the platform has to offer. Now, regarding data upload, I've created, well, actually, I've uploaded the data here in Python just to give you an idea. So 3 accelerometer axes, X, Y, and Z, and this is the target, so digit 0. And this data was collected at a frequency of 100 Hertz. So that means in 1 second or 1000 milliseconds, 100 different measurements have been taken. And there are 200 samples per each digit with 200 rows per each sample. Okay, so let's upload the data set. I've got it right here. It's this one. And we just drag and drop. Or you can select from storage. There is a data set storage. So everything you have uploaded previously for other solutions, you are welcome to choose from. And you don't have to upload your data set 10 times if you already have it in the platform. Okay, so the data set is uploaded. And let's click OK. And one last thing you want to do here at the data set tab is to select the target variable. So which column you want to learn to predict. And these are your columns, and it's digit here. So let's select digit and click next. We're done with the first step, very easy. And on the second step, well, there are quite a few settings here. So let's go from the top. So first thing here is the metric function, which is going to be used to select the best model. And these are the different metrics which you can choose from. So let's stick with default. The next setting here is input data type. So in this case, in the data set, all of them are integer 16. And now to the more important things. This really can be defined by default by the platform. Now, this is a digital signal pre-processing use case because our data represents a time series where throughout some part of that time series, you have performed some action. For example, when you have drawn a 0 in the air, this might have taken some time, maybe 1 second or 2 seconds. And throughout these 2 seconds, lots of measurements. In this case, with a frequency of 100 Hertz, over 2 seconds, 200 measurements were taken of the accelerometer X, Y, and Z values. So that means we have to break the data into windows where each window would represent each training sample. And so this is a windowing use case. The platform supports many other different use cases. Now let's select windowing. And here we have to define how many samples in your data set represent one digit. Let me quickly pull up the data set here. So 200 rows in the data set all correspond to this first example of digit 0. So because for over 2 seconds, with frequency of 100 measurements per second, that data was collected. So that means we need to tell the platform exactly this information. So what is the window size? And there are a few options on how you can do this. Just using the number of rows, you can say 200 rows is my sample. Or you can use some other heuristics here. For example, you know the frequency of your data collection. You know the frequency is 100 Hertz. And you want the window size of how many milliseconds? 2000 milliseconds. So that means we want 2 seconds of data that was collected at 100 Hertz. So that means it will take 200 rows from your data and use that as the training sample. And if you don't know none of that, and or maybe you want the platform to figure out which window works best, we have here an automatic option. So the platform will run a few experiments with machine learning and select the most appropriate window. Okay, so but fortunately we know exactly the values that were used for collecting the data. So here we have them set up. Now the feature extraction. So here are our three features, accelerometer X, Y, and Z. And we have here selected the feature extraction option. So by using this option here, you can define which features the platform will extract out of accelerometer X, for example. And there are three different sets of features. So the amplitude-based features, and they're enabled by default. Statistical features, and there are 11 features here. And frequency-based features, which you can select or deselect really individually for any of your axes or your features that you have in your data set. Now let's select all. For the first axis, for the second axis, we'll also select all, and for the third axis. But you are more than welcome to experiment with this any way you like. There's another option here. So this is feature extraction. Now feature selection. So after all those features, in this case, we have selected, let's count, 2, 11, 6. So that's 19 features will be created for each of the axes. So altogether, there's going to be 57 features. Now, for example, you have a very strict regulation for the model to be very fast or maybe very, very small. So you would like to use all the potential the platform has to offer, but with some intellectual feature selection behind the scenes, because maybe you don't need all of those features. Maybe some of them are more important than the other. So we've got two different methods that will select from all those 57 features, in this case, the most appropriate ones, the ones that are, that provide the best predictive power. And that will reduce the overall model size. And in many cases, it will improve accuracy just by removing the unnecessary noise. So here are the two methods. So one of them based on the correlation threshold between the two features, because since all of them are extracted, so 19 features are extracted out of one, some of them may be very much correlated to each other, and based on the correlation threshold 95% or 0.95, some of them may be deleted or will be deleted if you select this. And the other one is, this one is a bit more lengthy in time, but really it's not going to take not more than 1 minute in this particular case. Recursive feature elimination with cross-validation. So there's going to be three different machine learning algorithms. All of them will be independently assessing all those features and figuring out altogether which ones work best. So maybe let's select this. And in the feature selection here, we also have enabled the option to remove lag features, because by default, in the windowing use case, we are going to create lag features for each of the accelerometer axes. In this case, 200 lag features will be created. So 600 additional features will be created if we don't disable this remove lag features option. But again, if you have the necessary compute on your final end device that you're going to embed it into, you might as well experiment with this. Or maybe you have lag features enabled and you also enable some kind of method of feature selection or elimination, maybe this one, and it will create 657 features altogether. And this recursive feature elimination may easily eliminate 400 of them or maybe 500 of them. So there are lots of different ways you can experiment with this, and from manual selection to automated selection. So let's enable this. And last but not least, very important, the model settings. So here you need to select the parameters of your microcontroller where the model will be embedded into. So we support anything from 32 to 8-bit. And for the smaller microcontrollers, you can disable or enable flow data type support. So for 32-bit, well, you cannot disable flow data type support. So let's make this model the smallest possible, 8-bit for an 8-bit microcontroller without flow data type support. So these are all the settings. And here we are estimating, and we'll have a more accurate figure after the training will be done, the consumption of RAM by this model with this particular amount of particular window. Okay, let's start training. And we'll be staying here under the training tab, and everything will happen in this window. And right now, a virtual machine is being created. This will take some time, and after that, the training will start. And here we'll see the resulting. You don't have to wait. We can message you when this is done. So, and here you'll see the resulting metrics and their values with each iteration of the neural network, with each epoch. So let's not wait. I have the pre-trained model in this case. And okay, so this is the model that was trained yesterday. And as you can see, the training is completed. It's at 100%, and it took exactly 50 minutes. And despite the fact that we have selected accuracy as our target metric, we also calculate all the other metrics relevant to this type of problem for classification, that is, just for user convenience. And you can see how good your model is doing across all of these metrics. And if you don't want to interpret this, there is the model quality index plot that tells you how consistent the model is doing across all the metrics. And now for classification, this is, well, not as handy because in all the cases, but except for log loss, the best metric value is 1. And you can easily understand how good it's doing. But for regression, this is very, very, very important. And we've created a special mechanism to visualize the accuracy of the regression model like this. So after training, here we can see the total footprint estimation. So this model has been with accuracy of 0.91 or 91%. The model size is estimated at 1.4 kilobytes, and it has 404 weights. And these are the other components of the footprint. For example, the calculator in this case is 5.4 kilobyte. So altogether, the flash consumption by this model, including the model itself and the calculator, is estimated at 5.6 kilobytes. What's very important is that since the platform has done data pre-processing using these windows and feature extraction and the feature elimination and all those things that I've been talking about at the training configuration, all that code, all that C code will be generated together with training the model. And after the training is done, you will be able to download that model with all the necessary C code that will know exactly how to transform the streaming data and then to apply the model to this data, to this transformed data. So the training is done. We can proceed over to the predictions tab. And well, the most important thing here is really this button here, download a C library. And here you can see all the same results from before. Now let's just click download, and the archive with the model and with all the necessary code will be dropped into your downloads folder right away. So let's open this archive and see what it has to offer. Okay. So the actual model is here in the model H folder file. This is really a set of binary arrays which includes the model weights and biases and a pipeline for applying those weights. So the model is the whole content of the model is contained here. So the pre-processing steps are saved under the pre-processing folder, and feature engineering are saved here as well. We also, for user convenience, provide converted models, or in this case, yeah, with the DSP function where we are extracting the signal out of the window. We don't provide the converted models, but for other options, here, this folder will contain models, our model saved in ONNX, TensorFlow compatible format, and H5 format. Well, just in case somebody needs them, because we have our own proprietary format, a very simple just set of arrays and a calculator, this file right here. You can see this is a set of functions in C which will take your streaming data. It will look into the data pre-processing and feature engineering folders to perform necessary streaming data pre-processing. Then it will grab the model here and create predictions for you. And there is a short readme that explains how to embed this model, of course, along with the help of our embedded engineers. So that's basically it. If you guys have any questions, I can see there are some questions in the Q&A. I'll be more than happy to answer them. So you solve all the shown problems using only your kind of dense architecture, question mark, or are also convolution 2D used? Okay, our model is not a densely connected, and we would like to call it a sparsely connected swarm of neurons. So there is really no definition of layers in Neuton, and some of them may be connected, some of them may not be, and really not even all the inputs are connected to the neurons. Maybe some of the inputs may be connected to the neurons. It's very different from the traditional neural network, and that's why it behaves very well for regression and classification and digital signal preprocessing and audio data preprocessing use cases, because we've been creating this architecture, or not that architecture, but a framework with those problems in mind. And there is really not a defined architecture of a neural network when we have started training. There is no some predefined architectures that are selected. There is no network architecture search, like let's try this one, maybe then let's try that one. None of that is happening. Neuton is being built from scratch, and it creates the architecture by itself for every use case individually. And it always starts with a single neuron, even if you have like a 1600 inputs, and say you're working with some spectrogram or audio data. The Neuton model will start building itself from the single neuron, and then it would iteratively be adding additional neurons if necessary. And whenever it understands that the model starts to overfit, and one more interesting thing is that it's being trained under the constant cross-validation, which is also not usual for neural networks. So with this cross-validation process, once it understands that it starts to overfit, it stops the training process. And this way, you will not end up with a architecture that has been predefined with lots of redundant nodes. Every one of them will make perfect sense. And that's why they are so small. In one iteration, you don't have to try to build it once again, because in one iteration, it will create the most optimal model structure. So it looks like all the data is in one file. Are there samples separated in any way? Okay. Are the samples separated in any way? All the data is in one file. The current platform requirements is that you upload your data in a CSV file format, and we have a note that describes on the platform that describes on how to do that. In many different cases, you may be collecting your data with some other pattern, but ultimately you will need to combine it together in one CSV file. So yeah, it's one file. Also, you can upload your second file for the cases of if you want to validate on your holdout set. And I haven't showed it to you, but when I was uploading the data, there is an option to upload holdout validation set. In this case, there will be no cross-validation, and the model will be validated on a validation set. For audio data, we have a separate pipeline where you can work individually with folders and your WAV files in them. And there can be hundreds of thousands of individual WAV files. Okay, so that's it. Could the system support both unsupervised learning and supervised learning? Well, the algorithm can support unsupervised learning, and we're currently working on a problem of anomaly detection using our algorithm. It's a very interesting framework or like a branch of Neuton. It's not automated yet on the platform, and we are working individually with our customers with those with anomaly detection cases. But the platform is only supervised machine learning. So can these lag features also be removed automatically by their importance, like you have shown earlier? Sure. So the feature generation process is disconnected from the feature selection. So first, the feature generation process is performed, and everything that you have selected will be created for each axis. And then the feature selection will work on top of that and select only those that matter. And in some cases, I remember this very interesting use case, and it's a very well known, by the way. HSL is the use case short name. You can Google it. It's an open source data set for building a multi-class classification model for recognizing where the person is traveling in a car, on a bus, on a train, on a plane, on a bike, and there are 8 classes in there. And altogether, the data after pre-processing has been constituted from 468 features. Our recursive feature elimination pipeline has left 11, and the model was more accurate than the model that has been trained on the whole set of features. So yeah, in some cases it works extremely well. What C standard is used? I'm not sure that I understand the question. Could you please maybe elaborate more on that? Let me just skip to the next one, and maybe you can write in the Q&A. Okay, so does the flow support recursive layers like GRU or LSTM? No, it doesn't. And as I mentioned, there is really no layers in the neural network. This is a proprietary algorithm that has been patented by 2 patents across the world, and it doesn't support or doesn't have any layers. There is a really different structure, and you can read all about it on our website. And just for instance, one more other distinguishing thing is there is no backpropagation of an error. There is no gradient descent in this neural network. And the activation functions are also trainable parameters, which is very uncommon as well. So, and the common comparison to the open source is not really used with Neuton, because it's a very different framework. Okay, so could your model and code compile as a component, such as a voice recording system uses your VAD as a component? So I guess what you're asking is that, can you set up so we've trained the model, we've downloaded the archive with the model and the necessary data pre-processing pipeline. So can that set of code be used inside the voice recording system as a component? If that's what you meant, then it's just like embedding your code with the model into any other microcontroller. In this case, your microcontroller has a voice recording component, and so some kind of a microphone. So if I'm getting your question right, it's just the process of embedding your model into this microcontroller, and that will accept the data from the microphone, just the usual use case for Neuton, if that was your question. Okay, so Marcel has clarified the question. I mean, if you use Windows in the first place, you have to feed Windows into the model to inference, but you need a way to limit the windowing size, for example, through the 2-second time window, so you have to stop after every number. Could you make the window dynamic in case you write faster or slower, or is the size always the same after training? Could you make the window dynamic? Again, I'm trying to understand this question. So in our experiment, in order to finish drawing the digit in the air, it takes 2 seconds. If you use 1 second, you'll be halfway done. And there is really no digit, right? And there's nothing to recognize. So for this particular problem, for the digital signal pre-processing, if you have been recording your data with the 2-second intervals, then the 2-second window is necessary for you to really draw that digit. Maybe it's faster, maybe it's 1 second or 3 seconds. You can give it a longer window, but you can draw faster for different types of users that use different time to draw that digit. But this window has to be representative enough in order for everyone, or maybe only you, if you're the only user of this model, to be able to finish what you are what you are doing, so the model could recognize what you have done. Regarding the dynamic window, maybe I have another example for the audio data pre-processing, for instance. Say we've been using a window of 1 second to recognize the keyword. And in this case, at inference, it's not going to be listening to 1 second, then recognizing, then listening to the next second, and using the model for inference, and then another second. It's going to be a moving window and it's a configurable parameter. For example, you start your microphone, the first 1 second is recorded and predicted, and then every 25 milliseconds, another 1 second segment is being constantly listened to and used for predictions, so that you would not miss your keyword, because you may start saying your keyword 1.5 seconds after the microphone is on, and finish 2.5 seconds. And then if you will not overlap these windows, your first second will contain the half of your keyword, and the second will contain another half, and therefore the model will recognize nothing. So in this case here, we have a moving window. Again, if that answers your question. Okay, so Quentin has asked, does Neuton have built-in support to help infer the built networks on multi-core platforms by enabling parallel execution, enhancing communication between processing cores? So Neuton inference is why it is so fast and lightweight is just because it's very simple. It's just a set of nested for loops. So if you want to take advantage of a multi-core inference, you just have to rework the calculator. Again, we can help you do that. But since we've been creating the algorithm and the inference engine to be silicon agnostic, so we create a solution that works for all and works very well. But if you want to split the calculations into different cores, then this is just a matter of amending the code in the calculator, in the Neuton C file. So Annabelle has asked a question, is it possible to train a model based on decision trees instead of neural network and compare its performance against both? Well, we're doing that constantly, and not only the decision trees, but also all the other open source frameworks, neural networks, non-neural algorithms, and much more powerful than decision trees. For example, gradient boosted models like Lite, GBM, XGBoost, CutBoost, random forest, all the linear algorithms, and all the competition as well. Because we need to understand whether our product is any good. And we are doing that comparison for a few years now. On our website, there are benchmarks, and Blair has shown you some benchmarks in the presentation. So yeah, the platform does not provide the option for you to train another algorithm, but you're more than welcome to do that on your own and just compare the results. Okay, so Tobias, C standards are mentioned here. Okay, I've got your question. Let me, because I'm a data scientist, I work with Python, and our embedded engineers are working with C. Just give me a second. I'll get that question answered to you before we finish this demo. I'm already sending this to the guys, and I'll have an answer for you in just maybe 1 minute. And the last one, the moving window is something I'm trying to implement with Neuton right now. I'm trying to recognize written characters without stopping between the characters, so you can analyze handwriting. Well, you cannot really stop between the characters because okay, so let's do this again. So the moving window is something I'm trying to implement with Neuton right now. You're trying to recognize written digits. So if you're doing the same experiment as we have done by writing them in the air, then I guess not. So I guess you have for example, your microcontroller on your pen, and you're writing without interrupting, like with basically drawing a single line and drawing your words with a single line. But there still is a different letter which you have to recognize. And in this case, and some letters are longer in length to be written and some are shorter. Well, this is a more challenging task, I would have to say, because yeah, some of the letters, like for example, I don't know, O and W, they may take a longer or a different time to draw, but really for any character to be recognized, you have to give it a sample of you drawing that character. So the gyroscope could record how you have been changing positions of the pen when you are drawing this character, and you have to give many samples of each character. In our case, our engineer has collected 200 samples per each of the 10 digits, so 2,000 samples altogether. In your case, I would try to, try to use the automated window selection pipeline checkbox on the platform. Let's see what it will find, because in some cases we've noticed that the performance is much better than a human judgment, because by machine learning it runs lots of different experiments and then figures out which one works better. Yes, that's it. I'm still waiting on the answer on the C standard, and I already have our embedded engineer online. Just give me a second. I'll answer that question as well. So other than that, I hope I've answered all your questions. Okay, it's C99. I'm sorry for the hold up. So it's C99.
Awesome. Thanks, Daniil. And thanks, Blair. Blair, I know you answered a few other questions just sort of through text and on through the Q&A chat. Did you want to give us any summary or any wrap up before I close out the session?
We're pleased and happy to be able to kick everything off. As I say, be the tip of the spear.
Yep. Awesome. Thanks very much, Daniil and Blair. We have to, before we close, kind of again, thank our Tiny Machine Learning strategic partners, make all of these tech talks and webinars possible, and kind of help take our whole Tiny Machine Learning community to the next level. Just a couple of slides for each of the executive sponsors and the platinum strategic partners. But really appreciate everyone attending and taking a look. Just as a reminder, we do have a whole series of these deep dives coming up over the next few weeks and even few months, where all the participants of the TinyML, AutoML forum will kind of be getting deeper into their algorithms. But as we just said, we really appreciate Neuton going first and kind of this deep dive into all of the capabilities of their platform. So we thank everyone for joining us today, and hope you have a great day. Take care.